Welcome to A-Level and EP Physics. In today's lesson, we will discuss past paper questions from May-June 2023, Paper 4, Variant 1. In the last video, we have already discussed question 1 about gravitational field. Today's lesson, we will start from question 2 and we will try to cover all questions about mechanics and thermal physics. As always we do, we will discuss these questions in detail so you can improve your conceptual understanding of A2 physics and also you can have better understanding of these questions. Let's study together, let's improve together. Question 2 says a steel sphere of mass 0.29 kg is suspended in equilibrium from a vertical spring. The center of sphere is 8.5 centimeters from the top of the spring as shown in figure 2.1. The sphere is now set in motion so that it is moving in a horizontal circle at constant speed as shown in figure 2.2. The distance from the center of the sphere to the top of the spring is now 10.8 centimeters. For part A, we need to explain with reference to the forces acting on the sphere, explain why the length of the spring in figure 2.2 is greater than in figure 2.1. A beautiful question, a conceptual question. So read question, try to think about forces acting on the sphere in figure 1 and forces acting on sphere in figure 2 and then compare. So that's all what you need to do. So first of all, if you look at figure 1, in this case we have sphere. So if we draw the free body diagram, force acting downwards on the sphere, this one has to be mg, and force acting on the sphere upwards, this one has to be the tension T. And in this case, in the second case, there is also tension here, so we can draw this line here. So there is also tension is acting along this line, so we can say this one is T. Now if you look at this one, on the sphere there is a one force that is acting down, that force is mg. But this tension has two components. So one component of the tension, this angle is 27, so here angle, this angle also has to be 27 because alternate angles are equal. We can resolve this T into two components. So we can also draw one line here. So we can say this is horizontal component of tension. So this one is TH. And horizontal component of tension in this case is providing the centripetal force. So we can write down this one is FC. Horizontal component is providing centripetal force because this is moving in a horizontal circle. So in this case we can simply write down T is equal to mg. T is equal to mg. For this one, so you can see this is a triangle. So if you wanna draw an other line here, you can also draw the line here. So this is a triangle. So we can draw the arrow here. If you are more curious about this one, you want to see this one in a proper way, we can draw another line here. So this is vertical component of tension, so we can say this one is TV vertical. So this is also TV. I just draw here so you can see how forces are balanced. So in this case, along vertical we can say T vertical, this one is equal to mg, and T horizontal in this case is equal to centripetal force. So if we want to write down T here, T has to be equal to T vertical square plus T horizontal square and root of this. T vertical is equal to mg square. So this is mg square, means T vertical square plus T horizontal. We have this is centripetal force square and root of this. So this is new value of tension. I can say this one is T new, and we can say this one is T naught. T naught, you can say this is equal to mg, so we can write on here. So we have T naught square plus we have FC square. I hope now you can see from here it is very clear to you that T new, this one is greater than T naught. So T new in this case is greater than T naught because extra force provided by the spring is centripetal force. So spring in this case also is providing the centripetal force, means the horizontal component of tension in the spring is providing centripetal force. So that's the reason T nu is greater than T naught. If tension is greater, it means extension for the spring. If tension in the spring is greater, so let's write on here, if tension in the spring is greater, then spring has spring constant, so delta x also has to be greater because this is constant. If this increase, this also has to increase. So that's all what you need to understand in this way. If these concepts are clear to you, so let me show you the answer, how you can write down your answer. So you can write down these points in your answer. First point you can mention in this case, horizontal force on sphere causes centripetal acceleration. Mean horizontal force on sphere, this one is providing the centripetal force. And this is the horizontal component of tension. Weight of the sphere is now equal to vertical component as we have mentioned here, and greater tension in the spring, so greater extension of spring. So if T greater, it means delta x also has to be greater. I hope this makes sense to you. Part B says the angle between the linear axis of the spring and vertical is 27 degrees. So this angle is given to us, so we can also write down 27 here because alternate angles are equal. For part B1, we need to show that radius r of the circle is 4.9 centimeters. So it means that we need to show that this radius of the circle, this is equal to 4.9 centimeters. 4.9 centimeters. We have L is given, that is equal to 10.8 centimeters. So simply we need to understand this triangle. So we can form this triangle and we need to find out base of the triangle. So in this case, base of the triangle, this base is equal to r and this has to be equal to L sine of, because this angle is 27, so opposite side has to be sine, so this has to be sine of 27 degrees. L is 10.8 centimeters. So simply we can say r in this case has to be equal to L sine of 27 degrees. L we have, that is equal to 10.8 centimeters multiplied by sine of 27 degrees. So our final answer in this case will be 4.9 centimeters. Pretty straightforward one. Simply you need to understand how to form the triangle, then how to solve the triangle. For the second part, we need to show that tension in the spring is equal to 3.2 newtons. But we have already discussed forces acting on the sphere. We have discussed that mg is acting downwards on the sphere and the tension is acting on sphere along this certain angle. And we can resolve this tension into two components. We have discussed it as one vertical component. So this one is the vertical component and it has one horizontal component. So this one is the horizontal component. We can also complete this triangle for better understanding. So we can complete this triangle. So in this case, this is vertical component. An angle is given to us. Here we have angle. This angle is 27 degrees. So if this angle is 27 degrees, so this component of the tension, this has to be T cosine of 27 degrees because this is with angle. And this one will be T sine of 27 degrees because this is opposite to the angle. And so this component is T cosine of 27 degrees. This sphere is in equilibrium, it means forces along vertical, they are balanced, but sphere is moving in a circle, in a horizontal circle, so it means forces along horizontal are not balanced. So the resultant force on the sphere is this one and this force is providing centripetal force. But for this case we need to find value of tension only, so we can look at forces along vertical. Along vertical we have T cosine of 27 degrees, this one has to be equal to mg. So from here we can write down T, this has to be equal to mg divided by cosine of 27 degrees. So here we have m, that is equal to 0.29 kgs and value of g is 9.81 divided by cosine of 27 degrees. If we solve this one, we'll get T is equal to 3.2 newtons up to 2 SF. So this is how you need to answer this question. This question has 2 marks. The first mark you will get if you have written this equation. You will get 1 C mark even if your answer is wrong. But if you got the right answer, you will get 2 marks. Third part says the spring obey Hooke's law. Calculate the spring constant in newtons per centimeter of the spring. So we need to calculate K. So in this case, delta T, the increase in tension, this one has to be equal to K times delta X. We need to calculate value of K. So simply we can say K has to be equal to delta T divided by delta X. And delta T has to be equal to new value of T minus initial value of T divided by delta X. So from here simply we can write down T new. We have new value of T that was equal to 3.2 newtons, and initial value of T, if you look at this figure, initial value of T is equal to mg. So here we have initial value of T. So this one is T naught, and T naught, this is equal to mg, means mass of the sphere times g, and mass of the sphere is 0.29 multiplied by 9.81. And new value of spring we have, that is equal to 10.8, and the initial value of L for the spring we have, that is equal to 8.5, and the unit of this one is centimeters. So if we solve this one, we will get 0.15 newtons per centimeter. So this is our final answer, and this question has 2 marks. The first mark, C1 mark, if you have written this part, so you will get 1 C mark, and the second mark is the answer mark. If you got the right answer, you will get 2 marks. Part C1 says use the information in B to determine the centripetal acceleration of the sphere. And centripetal acceleration, this one has to be equal to the centripetal force divided by mass of sphere. So centripetal force we have already discussed actually, so let me redraw. We have discussed the force is acting on the sphere, mg is acting downward, and tension is acting at certain angle in this direction. So this one is the T, and this tension has 2 components. One is the horizontal component and one is the vertical component. So this one is the vertical component, and we have the value of angle here is equal to 27 degrees. So this is the T. This horizontal component is providing the centripetal force, so this is T sine of 27 degrees. So simply we can replace centripetal force in this case with T sine of 27 degrees, because centripetal force is equal to this 27 degrees divided by mass of the sphere is 0.29. So T is 3.2 newtons. So here we have sine of 27 degrees divided by 0.29. Now if we solve this, our answer should be equal to 5.0 meters per second up to 2 SF. So this is our final answer, and this question has 2 marks. If you have written this step, you will get 1 C mark, and if you got the right answer, you will get 2 marks. For the second part, we need to calculate the period of the circular motion of the sphere. So we have centripetal acceleration, so we can start with centripetal acceleration. Centripetal acceleration is equal to r times omega square, but omega is equal to 2 pi over t, means the angular velocity is equal to 2 pi over t. Now simply we can replace omega with 2 pi over t, and if we simplify this one, we will get this is r, and here we have this is 4 pi square over we have t square, and here we have a c. We can rewrite here, so we can say a, this is equal to 4 pi square, and here we have r divided by t square. For this question we need to calculate time period, so we need to make t the subject. So we can write down here, so this is 4 pi square r divided by a, and this is t square, so this is t square is equal to this, but we need t, so we will take root on both sides. So here we will get this is 2 pi, and here we will get r divided by a. Now simply we need to plug in values of r and a. A is the centripetal acceleration and r is the radius of the circle. Radius of the circle is equal to 0.049 meters, or you can say 4.9 centimeter, divided by 5.0. This is value of acceleration. Now simply we need to solve. If we solve this one, we will get 0.62 seconds. So this is the final answer, 0.62 seconds. And this question has 2 marks. 1 mark you will get if you have written this expression, you will get 1 C mark, and if you got the right answer, you will get 2 marks. Question 3 part A says, state the reason why two objects that are at the same temperature are described as being in thermal equilibrium. Let's try to understand this one with one simple example. Imagine that we have object A and this object is hot, and we have another object and this object is cold, and we can say this object is B, and they are at 2 different temperatures. So in this case, thermal energy will flow from hot to the cold object. Let's say this is 100 joules of energy. Some thermal energy from cold object will also flow to the hot object. Let's say this is 20 joules of energy. So in this case, there is net flow of energy from the hot object to the cold object. So it means that in this case, cold object is gaining thermal energy, so its temperature will rise. Now we can imagine a case when these two objects, they are at the same temperature. So we can say this is our object A now, and this is our object B. They have reached the same temperature. So let me clean this one. So they have reached the same temperature now. So this is object B. So this one is hot and this one is also hot, but they are at the same temperature. So delta T is equal to 0. So in this case, it doesn't mean that there is no thermal energy transfer when they are at the same temperature. When they are at the same temperature, there is no net thermal energy transfer, but still thermal energy will flow from A to B. Let's say this one is 60 joules of energy. Then from B to A, when they are at the same temperature, same amount of thermal energy will flow from this B to A as well. So in this case, A and B, when they are at the same temperature, they are in thermal equilibrium because there is no net thermal energy transfer between these two objects. So this is what is meant by thermal equilibrium. No net transfer of thermal energy between two objects when they are at the same temperature. I hope this one is clear to you. Now let me show you the answer. So this is how you can write on your answer. If you write on this one sentence, you will get 1 mark, and this is B mark, mean it has to be in your answer. Part B says figure 3.1 shows the variations with temperature of the densities of mercury and of water between 0 degrees Celsius and 100 degrees Celsius. Temperature may be measured using the variation with temperature of the density of a liquid. Suggest why for measuring temperature over this temperature range, mercury is a suitable liquid and water is not a suitable liquid. So first of all, we will look at this graph. If we look at this graph, we can see this graph is linear. If this graph is linear, so first thing we can say this one is linear. So one thing we can say about this graph, this one is linear. But if you look at this second graph, this graph is non-linear. So this one is non-linear. This one is linear, and also it has unique value of density at each temperature. So here we have one value of temperature, one value of density, and if we pick another point, let's say if we pick this point, at this point it has certain value of temperature and it has certain value of density. It simply means that each value of density is unique at certain temperature. So this graph is suitable, means mercury is a suitable liquid to measure temperature, but this is not a suitable one. If we draw a horizontal line here, so we can see at the same value of density, we have two values of temperature. So that's the reason this is not a suitable liquid for measuring temperature. And at this point you can see we have two values of temperature and we have one value of density, and also this is non-linear, so this is not suitable liquid. So these 2 points we have to mention, and this has 1 mark and 2 marks. Let me show you how you can write down your answer. So in your answer you can talk about these points. First one has only 1 mark. If you write down variation of density with temperature is linear, you will get 1 B mark. You can also say each temperature has a unique value of density, you will get 1 B mark. And for the second one, water is not a suitable liquid, you can say variation of density with temperature is not linear, as we have mentioned here is non-linear. Region where the density does not vary with temperature means at this point density is not vary too much with temperature, so you can also talk about this region. We can also say different temperatures have the same density, as we have mentioned at this point. We have one value of temperature, at this point we have another value of temperature, but the density is the same. So that's the reason water is not a suitable liquid. So this is how you can read the graph. You need to understand how to read the graph and how to get informations from the graph. So this question is all about reading graph. Part C says a beaker contains a liquid of mass 120 grams. The liquid is supplied with thermal energy at a rate of 810 watts. The beaker has a mass of 42 grams and a specific heat capacity of 0.84 joules per kg per Kelvin. The beaker and the liquid are in thermal equilibrium with each other at all times and are insulated from its surroundings. Figure 3.2 shows the variation with time t of the temperature of the liquid. For part C1, we need to state the boiling temperature in degrees Celsius of the liquid. So if you look at given graph, so we have the liquid, so we increase temperature of the liquid, then temperature of the liquid stays constant. So it means here this point is the boiling point, because here phase is changing, so we can say this one is the boiling point. And temperature at this point, simply we can read from y-axis. From vertical axis we can read temperature, and temperature in this case this is 75, so this will be 77.5 and this one will be 80. So let me write down here, so this one is 80 degrees Celsius. So simply you have to write down 80 degrees Celsius, and this is B mark, mean it has to be in joules. Part 2 says determine the specific heat capacity in joules per gram per Kelvin of the liquid. So we need to determine C for the liquid. We can say C for the liquid. This has to be equal to Q supplied to the liquid, means thermal energy supplied to the liquid. So we can say thermal energy supplied to the liquid divided by M times delta T, the rise in temperature. So in this case Q liquid we don't have, so we can leave that part. And mass of the liquid we have, beaker contains liquid of mass 120, so we can write down this is 120 grams. And rise in temperature we have from 25 to 80, so we can write down 80 minus 25. So we need to find out Q liquid, but in this case we can find out Q total. Q total has to be equal to Q supplied to the liquid, so we can write down Q supplied to the liquid plus Q beaker, and thermal energy used to raise the temperature of the beaker. We need to find out in this case Q liquid, so we can rearrange. We can say Q liquid, this has to be equal to Q total minus Q beaker. So this is beaker. So Q total we can find out because we have the time and we have the power. Power is given to us, so it means P times T. So we can write down 810 watts multiplied by 21. This is the time. And Q for the beaker, this one has to be equal to mass of the beaker, MP, C for the beaker times the rise in temperature of the beaker. So here we will have 810 times 21 minus, Mass of beaker 42 gram. So we have 42 grams multiplied by C for the beaker we have, this is 0.84. Be careful with the unit. So this is given in joules per gram per Kelvin, so it means this can be gram, but if it is in kilogram you have to convert this one into kilogram. So we have C, and the rise in temperature we have, that is 80 minus 25, because beaker and liquid, they are in thermal equilibrium, they are at the same temperature. So this is value of Q supply to the liquid. Now simply we need to write down here, so we will be writing here 810 times we have 21 minus we have 42 multiplied by 0.84 times we have, this is 80 minus 25. So we can use double bracket here. Now if we solve this one, we can find out value of C for the liquid, and this one has to be equal to 2.3 joules per gram per Kelvin. So our answer is 2.3. A beautiful question, how to answer questions about thermal capacity, means specific thermal capacity. A beautiful question. Part D says the experiment in C is repeated using water instead of the liquid in C. The mass of the liquid used, the power supplied, and initial temperature are unchanged. The specific heat capacity of water is approximately twice that of the liquid in C. The boiling temperature of water is 100 degrees Celsius. On figure 3.2, sketch the variation with time t of the temperature of the water between t is equal to 0 and t is equal to 60 seconds. Numerical values are not required. So first of all, if you look at the graph, we have temperature and time. Temperature on y-axis and time on x-axis. So we can write down the gradient. Gradient of this one has to be equal to the change in temperature, delta theta, divided by change in temperature. We can say this is delta T. For this one, specific heat capacity is given to us. So we can write down Q has to be equal to MC delta theta. Power is constant, so we can write on Q in terms of power, mean P times T, or we can say P times delta T. Interval of time thermal energy is supplied, so we can say this is P times delta T. So here we have MC delta theta. C is given to us in this case, so we can write on this one in terms of C. We can say this is P divided by M, and here we will have delta T divided by delta theta. Now if we compare this part with the gradient, we can simply write down, in this case C is equal to P divided by M times 1 over gradient. So this is the main point. So delta T over delta theta, this is equal to 1 over gradient. For this question, it is given to us C for water, this is double. If this is double, this one has to be half. So this has to be half. So we can write down here, gradient of new line, it has to be half. So it has to be half. So this is the main point. So let me circle this one. So this is the main concept you need to sketch line. Gradient has to be half. Now we will look at the same interval of time, mean here we have the same interval of time until here. If the gradient is half, it means the rise in temperature has to be half. So if you look at the previous line, so here we have the final temperature, this one is 80. So the rise in temperature, you can also see we have one big square, we have another big square, and we have two small square here. So half of that. So we have 10, this is 10, 20, 22. So 11 means until here. Until here. So if we choose this point on the line, that line should have half the gradient. Now simply we need to connect this one by the straight line. So we will start from here and we can connect this point and just draw the straight line connecting that point. So it is here. So this is the boiling point of water, and after that it has to stay constant. So this is how you need to draw the line. So the main concept is this: gradient has to be half. So first of all, I have found this one, gradient has to be half. If gradient has to be half for the same interval of time, change in temperature has to be half. So here we have found change in temperature is half. Then we have drawn just straight line. And when it has reached the boiling point, temperature after that has to be constant. It's a beautiful way to answer. Try to do this one again if once it is not clear to you. Very good question to practice graph.